Hello everyone. In this video, we are going to talk about hydrostatic forces, a topic that you see in statics. And before I start, I want to mention that the pictures you see are taken from this very, very great book, Engineering Mechanics Statics by Miriam and Craig. This is one of the absolute best statics books out there, and I bet everybody knows about it. It's one of the best textbooks. So these pictures are taken from there. So if you have an object inside the water and it's not moving, it's a static object, it's definitely exposed to the pressure underwater. And that pressure, when it's applied to some surface, it will create some force. So we're going to analyze that force, the magnitude of it, where is the equivalent or resultant force of that is applied, and look at some problems involving that. We're also going to look at the buoyancy force. When the object is submerged, there will be some force due to the basically displaced volume, and that will affect stability of the objects that are submerged, like a ship. So we're going to look at the center of buoyancy. And then there is another point called the metacenter and metacentric height and stability of that, and we're going to look at a problem involving that as well. So let's get started. So here we look at, if you have an object inside water, the forces that you can see on, let's say, the surface of the object AB, this top surface, is the result of the pressure. And as you know, the pressure inside water is increasing as you go underwater. Let's say this is the surface of water, right? And as you go down, if the pressure here is P naught or P of the atmosphere, when you go down by a height of h, the pressure here is equal to whatever it was on the surface plus the density of this fluid, whatever it is. So let's say water, whatever, rho of that fluid times g of the gravity times what? Times the depth in the fluid. Okay, and this formula is what you know from physics, so that's nothing new. Now here, if you want to look at the resulting force on the object, if you neglect this small p naught, right, compared to the rest of it. Now, not always this P naught is small, but many times, depending on this density, it could be actually much smaller than the pressure you see at some depth of the part. Okay, so here we're just going to look at the relative pressure, not the absolute one. So when you look at this surface of the object like this, at each element dA, if you look at some small element dA, there is some pressure, and this pressure, as you can see, is rho gh, right? So if we want to calculate the equivalent force dF is going to be that pressure P times the area dA, which is this guy here, and then you integrate it over the whole surface to get you the whole resultant force. So it's integral of rho gh dA. Rho and g, you can take them out, okay, if you assume the rho is constant and the material is not compressible, that fluid, then the integral of h dA, you're going to replace it by a times h bar, where h bar here is the depth of the centroid of that planar surface. Okay, so if you know where the centroid of the surface is, the height of that is used in this resultant formula. Okay, now the important misunderstanding is this. You might say, if somebody says, how much is the resultant force on this surface? You say rho g, the area of the surface A, times h of the centroid, right? So if the centroid is here, then this height of it is going to be what is going to be used in this R formula. But if they say, where does this resultant force pass through? Which point is the point that this resultant force is passing through? The answer is not the centroid. The point where this resultant force is equivalent, this equivalent force is acting on, is not actually the centroid. It's a different point that we call it the center of pressure. Okay, that is where this resultant force is acting. Why? Because you see that pressure is not constant and it changes by h. So as you go down, the pressure builds up, right, in a linear manner. So if you have here some constant value, right, let's say this much, as you go down, this pressure starts to what? Starts to build up in a linear manner, and so the center of pressure is not going to be at the centroid. Now, where is that going to be? Let's take a look. So if we want to find where the resultant force is going to go, at least if you look at it in 2D, you want to just find the height of it. So if you call it h of center of pressure, that is going to be what? That is going to be the formula that we always use for a centroid, right? That's going to be the, this is the force, right? So you take the dF, the force, multiplied by h, right? So this is the first moment of that force with respect to, of course, the x-axis, right? So you have this, and let's say this is your x-axis, this is your y-axis. So this force that is acting here, this dF, is acting on a patch that is in height h. But now, if it's here, that is a different h. And if it's here, that is a different h. So you calculate these moments of these forces with respect to the x-axis, the first moment of them. So it's going to be the distance of that force or that surface patch to the x-axis, which is h, multiplied by the force, and then divided by the force, of course, the integral of both cases. And that is going to be something like a y bar, basically, right? So this is how you find, remember in statics, we always had y bar was the integral of y dA divided by integral of dA. And that's the exact same thing here, except we replace y by h. Okay, so now if we move on from this formula, for P, we're going to replace it by rho gh. And the same here. Now clearly this is the resultant force, which is going to be rho ga h of the centroid, which here in this top formula I showed it by h bar, so that h of c is the same as h bar. But for the top one, the rho g comes out, but here you have h squared, so it's going to be the integral of h squared. And you know, integral of h squared dA is the second moment of area. So this is going to be the second moment of the area for the whole surface with respect to the x-axis. And the way we do it is, instead of calculating it with respect to this x-axis, we bring our axis through the centroid of the object, the surface. So if this is the surface, we calculate it with respect to this axis, this x prime, okay? Because for any surface, we always have the moment of the surface with respect to the axis passing through the centroid. And to go from x prime to x, we use the parallel axis theorem. So the moment with respect to x is going to be the moment with respect to x prime, plus, of course, the area of the surface times the distance between them squared. And this distance here is called hc or h bar in this case. So if you use parallel axis theorem, this numerator thing is going to be the IC. This IC is the, as I said, moment with respect to the axis passing through the centroid. So it's like this. And then the distance between centroid and axis and x, which is hc or h bar squared times a. So this is exactly parallel axis theorem. And so we're going to plug it up here. Now look, you have the same rho and g in numerator and denominator, so you can get rid of the rho and g. So in the numerator you have this guy, in the denominator you have AHC, and that's what you have over here. And if you want, you can get rid of 1A and HC. Here you're going to get just the HC, here you're going to get this one. So what would you see here? You see that the center of pressure is equal to the location of the centroid plus an extra thing. And this extra thing is always positive because the second moment is positive, A is positive, H is positive. So what does it mean? It means HCP is always bigger than HC. In other words, the center of pressure is always below the centroid. Okay, it's deeper than that. And so it's always what? It's always below that, which you can get it from this formula, or you can do it by simple geometry, as I'm going to show you in the next example that we're going to see. Okay, so this is the resultant force, and this is the location of that. So let's look at some examples here. First example, here we have a vertical gate. There is a lot of water behind it with a depth of 3 meters. And here, to keep it from swinging back, we have this small support at B, right? And this is going to apply a normal force in this direction. So this guy is not going to swing back and open up. Okay, so we are keeping the water behind this vertical plate. What you need to find here is the resultant force of all of this body of the water on the vertical plate and this normal force at B. So if I draw the free body diagram of this vertical plate in this case, right? So if this is my vertical plate here, what forces do I have on it? Well, I clearly have the force of the gravity on the plate. So this plate has some weight, which is not given to me in this case, but that's something like this. There are two forces at the pivot, so I can call them AX and AY. There is a resultant force from the body of water, which here I call it R. And there is a normal force from B. So this is the free body diagram of this body of water. Okay, what do I do now? First, how much is R? Based on the formula I showed you, this is equal to rho times G times H bar times A. So if I know where the centroid of basically the body of the water is, okay, and then multiply that by rho GA, that will give me all I need. So in this case, this is the body of water, it's 3 meters, so the centroid of that is right here. Now pay attention, this centroid is different than this one. This is the centroid of the whole object. This is the centroid of what? The body of the water, right? Because not all of this body is submerged. This much of it is above water. So that H bar is the H bar that I'm going to use not all the way to A. Okay, and this is water in this case. And this gate, of course, has a third dimension, right? So it is something like this. And the width of this guy is given to us. In this case, let me find it. So it is 6 meters wide. So rho is going to be 1000 and G is 9.81. And H bar here is 1.5. And A here is this 3 times 6, correct? Because one side of it is 3, the other side is 6. So if you plug everything in, you're going to get basically 265 kilonewton. Okay, again, this rho is 1000 here. kilogram per meter cubed. So that is the resultant force. Okay, so we got the first part done. Then it says, what's the normal force at B? And let's find that. And it seems like there is a small typo here, so let me fix it. So for that, I can take moment about point A. Why? Because those two forces would go away and the mg goes away. So here I'm going to take some of the moment about A. Let's say counterclockwise positive. So that means the R force is going to be sometimes distance positive and the B force is going to be negative. Now B force is exactly 4 because the distance is 4. This is equal to 0. So the question now is, what is this distance? Where does this resultant force act on this object? And this is that center of pressure here. So there are two ways we can solve it. We can find HCP, okay? One is using the formula I showed you. The second one is just by simply drawing the pressure profile. So you know the pressure profile, you start from basically 0 here and increasing linearly like this, right? So this is what you do. And from statics, you know that if the shape is a triangle, the centroid of a triangle is basically 1/3 from the base, 2/3 from the top. So it is here. And if this is 3 meters, then this portion here is 1 meter and this portion here is 2 meters, right? So all I need in this case, the distance from B to A is going to be what? It's going to be 2 meters plus 1 meter. So this guy is what? 3 meters. Pay attention. In this case, the centroid from A. What's the distance of centroid from A? It's 1 plus 1.5. It's 2.5. Right? So you see H of the center with respect to A is 2.5 meters. But for center of pressure is 3 meters. You see it's always below that. And from here, you should be able to solve for B, and that is going to be 198.7 kilonewton. There we go. Okay. So this is an example of an object under water. And basically finding the resultant force. In this case, I don't even need to go with this formula, but if I did, this portion here is exactly that extra 0.5 meter. Okay? So you can check it for yourself if you are interested. Now, if the surface is a different shape, you can still use these formulas because for these formulas, you see, we did not assume any specific shape for the surface. So when we found the formula for the size of the force and the location, we did not assume any shape. So ideally, they should be used for other shapes as well. Now, one thing we have here is the buoyancy force. So what is the buoyancy force? You probably all know about it. You all experienced it when you go for swimming. You feel like something is pushing you upward and reducing your weight. You feel lighter in the water. And that is because you are displacing a portion of the water by going inside the water, and the weight of that volume of water that is displaced is the buoyancy force that is going to be applied upward to you. So the buoyancy force is, as I said, the weight of the displaced water. So it's rho g times volume that you displace in the water. Okay? Or in this case, it could be V of submerged. Now, you might ask, is this buoyancy force something different from the hydrostatic force? No, it's the same thing. Except that here, the difference is, if you look at this example here, you see that only one side of the object, in this case, is exposed to the water. So the fluid is on one side of the object, not on both sides. So it's not submerged. It's just putting pressure on that wall on one side, not on both sides. If here you had something like this example here, look at this. In this case, when the water is on both sides, clearly you have pressure on this side of the object, and you have pressure on the other side of the object. And the difference between them is going to be this volume times rho times g. So it is purely the result of what? The result of difference of the hydrostatic pressure on different surfaces. Okay, so that's clearly that one. For instance, in this example, look at the ship. So let's say this is the hull of the ship. This is the cross section of it. If you look, let's say these two are vertical, this one is horizontal. So here the pressures are like this. So they are only horizontal components which can cancel each other. But on this surface, these are like this, and they are not canceled by anything. So when you add them and integrate them, that is going to give you the buoyancy force. Okay, yes? Now, if you tilt it, what's going to happen? If you tilt it, now you have a little bit horizontal here, more horizontal here, and some forces at angle here. Okay, yeah? So now the horizontal component of these forces at angle with these smaller horizontals would cancel these bigger horizontals. So the object is not going to move left and right much, but the vertical component of these again are not canceled, but since they are shifted, and not only shifted, now because the pressure increases, if this is like this, as it goes down, they get bigger and bigger. So because you have this linear distribution, now the center of them is not going to be here in the middle, is going to be shifted a little bit down, as we just learned. So now your buoyancy force is going to be what? A little bit to the right of the middle of the ship, not exactly what? Not exactly in the center at is what's in this symmetric case. Because these are all at the same height here. Now these points are not all at the same height. Okay, so what happens when some wave come in and your ship starts tilting? Would that gonna go completely upside down and it's gonna sink, or is it gonna bounce back and basically have some lateral vibration, right? Which is what you see. For most of the ships, it's not just gonna go down by some simple wave or some simple tilting. So why is that? What's going to happen? Let's talk a little bit about the ship stability in this case. So if I clean this, I can explain it a little bit better for you. So as I said, if you look at the ship free body diagram, there is the gravity force, mg, and there is the buoyancy force. When it's perfectly vertical, the buoyancy force and the gravity are aligned. So some of the moment about the gravity is zero, so it's not going to tilt. Now, if it tilts a little bit this way because of a wave or something, now, as I said, your buoyancy force is going to be further down to the right. Your mg is down here. Now, these two forces are not aligned. So what's going to happen? If you take moment about the gravity this time, you see that the moment of buoyancy force is counterclockwise while you were tilting clockwise. So what's going to happen? Because you are tilting clockwise, the moment is the opposite. This moment tries to bring back the ship to the upright position, and that's what makes the ship stable. So when you tilt, the moment of the force is going to bring you back upward and make you stay vertical. This is a stable scenario. But there are scenarios where your buoyancy force, instead of being on the right side of the gravity, like in this case, you see it's tilted clockwise, but your buoyancy force is a little bit to the left. of the gravity, this time this force will also create a clockwise moment that makes this guy go further down, and that is where this guy is unstable. So this is going to go capsized and it's going to sink, but this one is stable and it's going to go back vertical. So it depends on whether this buoyancy force goes on the left or the right. Another way that some people analyze it is they say the location where the line of action for the buoyancy force, this vertical line passing through the buoyancy force, and the line through the middle of the ship, so this line and this line, the location that these two are intersecting, that point M is what they call the metacenter of the ship. Okay, so what is it called? It's called the metacenter. Now, the distance between the metacenter and the center of gravity, this h, is what we call the metacenter height. Okay, so we have what? We have metacenter and we have metacenter height. Now look, in this case, your metacenter height is a positive number because the m is above the g. In this case, if you look, your metacenter is below the g, so this h, in this case, I can say is like negative. So based on this height of the metacenter, you can see whether if it's below it or above it, also if it's stable or not. Now, one of the interesting things that they do when they design a ship is to try to keep the metacenter at a fixed number. So they design the ships such that h is almost constant when the tilt angle alpha is up to 20 degrees. So for up to 20 degrees, they design the ship body such that the metacenter height stays constant. So with the same kind of moment, right? Because the amount of moment that you get to go back to or upright position is proportional to this h. So, or to this height, to this one, because also this one is related to h through alpha, that they try to keep it almost what? Almost constant. So that determines the stability of what? The stability of the ship. Now, let's look at one more example here. So in this case, we have this basically pole in water. And this pole is kept inside the water because it's like made of wood. So we won't let it go on the top of water and float. We keep one side of it down, pin it down to the ground by a cable, like that. Because of that, this cable will get some tension, and because the pressure is different on this surface of the object, right? So if it increases in a linear manner, right? So it gets bigger and bigger as you go down, then this pole will be at a tilted angle theta. The goal is to find the tension in this cable here and the tilt angle of the pole theta. So how do we find it? Okay, first of all, this is water again. So we have the density of it. The next thing we have about this pole is it is 8 meters. So this pole is 8 meters and 0.2 meters in diameter. So if I want to talk about the pole, that's 8 meters long, 0.2 diameter meters, and it is 200 kilograms. So these are the data for the pole. Okay, and The rest of the information is provided on the picture. So 10 meter, the depth of the bottom of the water. 5 meter is where the bottom of the pole is cabled down to the lake or to the bottom surface. So these are the information you have. Okay, now if you draw the free body diagram of this pole, so here at the bottom you have a tension, right? At the center of gravity you have the mg, and at the center of pressure you have the buoyancy force. So this is what this is, this object. So first of all, you need to find the buoyancy force, F of buoyancy. Remember, the formula is rho GV of displaced. Now here, because again you have the surface of the object on both sides, on this side and this side, the resultant of them is simply the buoyancy force, and we do not need to basically calculate this force on both sides and subtract. The subtraction, the result of that is the buoyancy force. So what we need to calculate is rho G and volume displaced. Okay, now rho is 1000, G is 9.81, and the volume displaced, we have to find it in this case. So first we need to know how much is this length here. If we find that and then multiply it by the cross section, right? So if I call this L, that's going to be L times cross section, which is pi d squared over 4, and d is this, and this is not L, this is L of displaced, because the actual L is 8 meters. Okay, so how do I find the displaced length in the water? Can I find it? Well, not that easily, because I don't have the formula for it, right? Because it depends on this angle theta. But if I take moment about this point here, this bottom point where it's attached to the cable, that can help me. So if I call this point here where it's attached to the cable, call it point A. This is a static object. I can take some of the moment about A and set it equal to 0, right? So in this case, what do you have? So here, this distance from here to here, this is half of the length, so that is 4 meters. And this distance is also 4 meters, right? So if this distance here, I call it x, which I don't know, and L of the displaced is 4 plus x, then I can say that the moment of mg, right, the moment of mg for point A is clearly clockwise, so it's going to be negative mg. And what is your moment distance here, or moment arm? That's this distance here for mg. Now the radial part of it is 4, and this angle here is theta. So if you look at it, it's a triangle like this, where this angle is theta and this distance is 4. So this one here that we are interested, that is 4 times cosine theta. Okay, this is the moment of mg. For B is positive, it's plus f of B. Now to find the arm for B, which is basically this distance here, we need to know where B, f of B is acting. Where is this point here? And for that, I need to go back and we look at this buoyancy force. So I told you about the magnitude of the buoyancy force, rho g v of displaced or v of submerged. Where does the buoyancy force act? That's the question that we need to look at. and then we can go and answer the question. So where does it act? The answer is this. The buoyancy force is passing through the centroid of the displaced volume. So here, if this is the displaced volume and this is the centroid of that, the buoyancy force is passing through the centroid of the displaced volume. In this case, this is the displaced volume and the centroid is here. So it is going to go pass through that. So this B prime here is the centroid of what? The displaced volume. And your buoyancy force is always passing through that. So if we go back and look at, in this case, the displaced volume is basically this part that is inside the pole. And where is the centroid of that? Well, the total length of it is L displaced, so it's going to be L displaced over 2, right? So this distance here, if I can do it right, this is going to be that L displaced over 2. So how much was L displaced? We just found that L displaced is 4 plus x. So this is going to be 4 plus x over 2. Okay? Yes? But not just that, times cosine theta. Because 4 plus x over 2 is the radial distance. We are interested in this portion, which need to be multiplied by a cosine theta. And this is equal to what? Equal to 0. And remember, this is 4 plus x. So if I plug in this number that I found for FB, which is a function of x, and plug it into the sum of f moment about a equals 0 and solve for it, cosine theta would cancel. The only unknown in the problem is x. You can solve for x. And if you solve for it, you're going to get 3.14 meters. Okay, in other words, the displaced volume, the displaced length is 4 plus x, which is 7.14 meters. So out of 8 meters, 7.14 of that is underwater to keep it completely stable. Okay, and statically at equilibrium. Okay, now that you found it, how would you find the angle? Where for angle, we can easily do a simple geometry. How? Well, look here. So if you look at this triangle here, for that I might need to do a little bit cleanup because it's too busy. So I do a little bit cleanup. There we go. I can look at this triangle here. Right? How much is this? That's 10 minus 5, that is 5. This angle is theta, and remember this one is basically 7.14. So that should not be very hard to find. Theta is going to be sine inverse of 5 over 714, and the answer is 44.5 degrees. There we go. So we found the angle. And now we can go about the tension. How do you find the tension? Well, remember that this was your pole. What you had was a tension here. What you had was mg here. And what you had was a buoyancy force, correct? So this is what you had. And here all you need is to say some force in the y equals 0. Which is basically FB minus T minus mg. This is equal to 0, and since mg is a fixed force and buoyancy force, now you have it because now you have the L displaced. You plug in everything and you should be able to find the tension force. So if you do it, it should be 238 Newton. Okay, and that is your tension. Okay, so hopefully this brief overview of hydrostatic forces and center of pressure, metacenter, center of buoyancy, right? Remember this point B prime here, this guy that the buoyancy force is passing through, that is called the center of buoyancy. Hopefully review of these with some examples was useful to you, and I'll see you in the next lecture. Thank you.